Consider a capacitor of width W, length L, and separation D, into which we have put two different dielectrics, kappa 1, which fills entirely a region which is x wide and W long, and kappa 2, which fills a region which is L minus x long, or the rest of the capacitor, and then also the width W. So we've completely filled the capacitor with dielectric, but it's two different dielectrics. And we'd like to say, is there a way of finding some equivalent dielectric constant that would be the same as these two, that would give us the same behaviors? So to do that, we want to walk through and do a couple things. We want to say, well, the capacitance of the the capacitance of the capacitor with nothing in it would be epsilon naught times the area, which of course is LW, over the separation D. Right? No big deal. But the capacitors are going to split basically, the dielectrics are going to split the capacitor in such a way that it looks as if it were two separate capacitors that are in parallel, because they're next to each other. But one of them filled entirely with kappa 1, and the other filled entirely with kappa 2, like that. And we'd like to say, is there some equivalent capacitance that would be just filled with some third capacitance, which I'm going to call kappa equivalent. So as a reminder, we have kappa 1 and kappa 2 here. So the question is, can we find that equivalent capacitance? And the answer, of course, will be yes, or we wouldn't be doing this exercise. Notice that for the one on the left, the blue one, we could say something like this capacitance is, call it C1, is kappa 1, because that's filling it, times the vacuum capacitance of this capacitor, which is only a mental capacitor for us, but it's still a thing we can talk about, as if that were filled in vacuum, which is easy enough to do. So we'd say, well, that would be epsilon naught, and it would be the width of the capacitor times the length of the capacitor over the distance. And then likewise, C2 would be kappa 2 times epsilon naught times the width of the capacitor times the length of the capacitor, which is L minus x, over the distance. And we'll use those moving forward. Since these are in parallel, we know that the equivalent capacitance is just the sum of the two component capacitors. So something like that. So it ends up being something like kappa 1 epsilon naught omega x over d plus kappa 2 epsilon naught over d L minus x, right? Which is no big deal. But then we know that our equivalent dielectric, well, the dielectric is always just the ratio of the new capacitance over the vacuum capacitance. So here it's going to be kappa 1 epsilon naught Wx over d plus kappa 2 epsilon W L minus x over d over the original capacitance in the vacuum, which was epsilon naught WL over d. So let's write this out, that kappa equivalent is, and factor some things out. We can factor out epsilon naught, a W, and a D out of the top bit, and we're left with kappa 1 x plus kappa 2 L minus x. And on the bottom, of course, we have epsilon naught WL over D. And it should be pretty easy to see these guys cancel out. And we're left with kappa 1 x, x over L plus kappa 2 L minus x over L. which was suggested by somebody that this is basically just the weighted average of the dielectrics. So that we can write the equivalent kappa dielectric is the first dielectric times the fraction of the length that it occupies, plus the second dielectric constant times L minus X over L, which, if you look at it, really is a weighted average of the dielectric constant, and the weights are the fraction of the length that they occupy.